Okay, problem 4. I've started drawing the diagram again. It's where we have Tarzan standing on a tree branch 10 meters up. He's watching Jane down the ground below. There's a vine hanging next to him. This is sort of Tarzan's, like, jungle furs loincloth. And I guess it would only be polite of me to give Jane something to wear, too. So anyway, there's Jane. Anyway, whatever. Okay, Tarzan's mass is 80 kilograms. Jane's mass is 60 kilograms. And so everything's just great. And then Tarzan sees, I think I said it was a rabid elephant. So there's an elephant. I don't really know how to make a rabid elephant. It's more like, this looks more like the Republican Party is attacking her. But anyway, okay. So the rabid elephant is attacking Jane, and so Tarzan is going to swing down to save her. So the first part of the question is when Tarzan swings on this vine down to ground level, and the vine he's chosen is at just the right height for him to be swinging horizontally when he gets down there. So he's got some kind of speed when he gets down to the bottom. So I'll call that VT. Okay, it's going that way. Okay, so what is that height when Tarzan swings down on his vine? Okay, so let's do an orange. I'm going to call this stage 1, or state 1, sorry, and this state 2. So this is when Tarzan is swinging horizontally right behind Jane. Strangely, he's shorter than Jane. Even though he's taller up here, he's now shorter than Jane. But anyway, this is state 2, and he's right about to hit Jane. Or right about to, save Jane, sorry. So let's see, in state 1, he has gravitational potential energy. I'm going to say gravitational potential energy is 0 at ground level. Okay, so he has gravitational potential energy equal to mg times this h that he starts at, 10 meters. He has kinetic energy equal to nothing. There's no springs or anything, so that's all our energy. So Emec equals mgh. Simple enough. And then when we get on to number 2, he's got gravitational potential energy of 0 because now he's down at ground level. Ek is 1/2 mass of Tarzan times v Tarzan squared. Jane is not part of this system. We're just talking about Tarzan here. So what Jane is doing at this point is entirely irrelevant. We're talking about Tarzan's energy here. And so Tarzan's mechanical energy is 1/2 mt vt squared also. Okay, so we assume no non-conservative forces, so we're going to take this mechanical energy here and set it equal to this mechanical energy here. Right here, mechanical energy conserved. And so what we get is, I'm going to do this over here then, 1/2 mt vt squared equals 1/2, oh sorry, not 1/2, mt, mass of Tarzan, times g times h. So what we're going to get then is Tarzan's velocity, or Tarzan's speed, is going to be the square root. Let's see, so that's square. So we brought this 2 over. I'm going to cancel m's. Sorry, I'm taking several steps here at once. Canceling m's, bringing the 2 over, and then vt is going to be square root of 2 times g times h. Okay, so let's see. So what is this going to be? So square root of 2 times, I'm using 10 for g because I'm lazy and I don't like getting out a calculator, and that's going to be, h is going to be 10 meters as well. So velocity of Tarzan is going to be the square root of 200, which is going to be the square root of 2 times the square root of 100. The square root of 100 is 10, so this is going to be equal to 10 times the square root of 2, and the square root of 2 is 1.42, I think. So this is going to equal 14.2 meters per second. So that's going to be Tarzan's speed when he gets down there. That was part A, okay? Now, for part B, Tarzan grabs Jane, who is also running at VJ. Okay, so Jane is running at VJ, which was less than VT. So this is VT here, so it's 14.2 meters per second. I think for B, VJ was equal to 10 meters per second. And Tarzan grabs Jane, and then how fast are they moving afterwards? So stage 3, we can say, here they are, and there's Tarzan, Jane. Just draw a massive double lines. You can see there's kind of 2 heads there, right? So this is 2 people. And so what's V for, I'm going to call it VTJ for V Tarzan plus Jane. Okay, so we want to find what that is afterwards. So hopefully this is not too complicated. So this is a collision. In a collision, sometimes energy is conserved, sometimes it's not. Sometimes mechanical energy is conserved, sometimes it's not. Depends on whether it's elastic, inelastic, all that crap. What is always true in a collision is that momentum is conserved. Momentum always conserved in a collision. So, momentum before was mjvj, so that's Jane's momentum, plus Tarzan's momentum. Okay, and that's going to equal momentum after. Well, afterwards, we got this clump of two people, which has a total mass of mj plus mt times vtj. Okay, so now this is actually fairly easy to solve for vtj, because we just take this whole mjvj plus mtvt over mj plus mt, and that's the unit. So what this is going to end up being is, let's see, so this is going to equal, Jane was 60 kilograms. Let's see, hang on. Jane was 60 kilograms going at 10, okay, plus Tarzan was 80 kilograms going at, from over here, 14.2. And then their total mass, so this is the total momentum of the system, total mass is 140 kilograms, 60 plus 80. So it's this, we take this 60 times 10 plus 80 times 14.2 is our total momentum, and we take that and divide it by 140, and find that they are moving at 12.4 meters per second. So VTJ equals 12.4 meters per second. Let me carve out a little space so we can do part C without having to move anything. Part C is simply, after this happens, they swing back up into the air. How high do they get on their vine before, so this is, I'll call this H sub F. How high do they get on their vine before, before they come to rest? So how high can they get above the ground with this? Well, this is actually basically just the first part in reverse. This is part A in reverse. This is the equation we found for part A. So this gave us Tarzan's velocity after he swung down as a function of g and his height. Now you notice that this doesn't depend on Tarzan's mass at all, right? Tarzan could be any mass at all, and this equation would still work. And if we simply apply this equation backwards, see, the great thing about conservative forces is that you can turn all your equations backwards in time and they still work. So if there's this much, kinetic energy down here, then it's going to translate into potential energy up here, and the math is all going to work out the same. So it's still going to work out that VTJ equals square root of 2g times h final. Okay, this is just taking their speed here and translating into how high they get. So if we square both sides, but see, now we need to solve for h final is the only difference. But that's easy. Square both sides. VTJ squared equals 2g h final. Okay, and then what you get is h final equals VTJ squared over 2g. Okay, and so our VTJ squared, that's this 12.4, 4 squared divided by 2 times 10 gives you 7.68, so 7.69 or 7.7 meters. So final height is 7.7 meters, and that is all.